Hi students. The last session we talked about the coordination complexes. So we gave a brief introduction about the Werner's theory, how he started, and the VBT theory, the limitations in the VBT theory. These are all we have looked in the last session. So it is also important to recap that the d orbital gets splitted into two subsets T2G and EG. So where this is in between the axis, this is along the axis. So you have a barycenter. So you have a stabilization effect, you have a destabilization effect. So these are the things we need to recap. And as I said, how much it is stabilizing, that much it should destabilize. That's the reason we have 0.4 stabilization and 0.6 destabilization. Okay. So as we said, the parameters which affects the d orbital splitting, oxidation stage, higher the oxidation state, higher is the splitting size of the d orbitals. Higher the size, higher is the splitting. So geometry, again an octahedral complex will have a higher splitting compared to tetrahedral complex. So in addition to this, there is another important parameter, that is ligand. So ligand also can have a huge impact on the splitting of d orbitals. So the variation of this particular magnitude of the d orbital splitting, that is delta. So this also depends on the nature of the ligand. So this can be, formulated using the spectrochemical series. So by following the spectrochemical series, it is easy to predict which ligand will split d orbital how much. For example, when you have a weak ligand, this splits the d orbital to a smaller extent. But then when you as we go from the left to right hand side, so we have halides, we have oxygen based nucleophiles followed by nitrogen based nucleophiles. They are moderate, and then carbon based nucleophiles. So carbon based nucleophiles are much stronger compared to the other ligands. So weaker the ligands, the splitting is going to be smaller, and then when the ligand is stronger, the splitting is going to be larger. Okay. So let us have a better, closer look on it. Let's say this is the degenerate d orbital before the ligand approached the metal. So when the metal in the octahedral field, when the ligand started approaching in the octahedral geometry, you started seeing the splitting. So we have a barycenter T2G and EG. So this dxy is, so this is stabilization, this is destabilization. So as you can see, the gap between this T2G and EG orbital is smaller, so the splitting is small. So as we go to the higher and higher d orbital splitting, the gap between T2G and EG is widening. But remember, the barycenter, the center of energy, so how much ever it is stabilizing down, that much it will destabilize on the other side of the thing. So this is different d orbitals splitting at different environments. So weak field ligands, okay, so as I said, it is like fluoride, chloride, so they have a smaller delta. Okay, so what happens, for example, if you take the d4 system, d4 system means you will have 4 electrons. So the incoming electrons, the first electron will come to dxy, the second electron will come to dyz, the third electron will come to dzx. So the fourth electron will have two options. Either it will go and pair up in the dxy, or it can go to dx square minus y square. Remember, when there is a pairing of energy within the same orbital, it comes with a penalty. So that because there is the electron-electron repulsion, that also could have a pairing energy destabilization. So either the electron can go down and do a pairing, or it can go up and then it will lead to the destabilization. So there is a trade-off between these two. So if the splitting is very small, okay, if the gap between T2G and EG is small, the fourth electron tends to go to dx square minus y square. So the overall spin of this particular complex will be contributed from 4 unpaired electrons. That is, one from dx, second from dy, third from dzx, fourth from dx square minus y square. So as a thumb rule, when we have a weak field ligand where you have a delta O, this delta is smaller, that is a gap between D2G and EG is smaller, This will form always high spin complexes. As a vice versa, the strong field ligand, again, let's say you take the D4 system. The first electron will come here, dxy, second electron dyz, third electron dzx. But then the fourth electron has to go all the way up. So remember, this y-axis is the energy scale. So if it has to go to dx square minus y square, there will be a lot of destabilization. So the fourth electron prefer to get paired up here. So in this particular D4 electron system, under strong field ligand, you have already one paired, so you have only two unpaired electrons in the system when you have a stronger field ligand. So whereas in the case of weaker field ligand, you have four unpaired electrons. A spin contributed from four unpaired electrons. That's why we call it as an high spin ligand complexes. Whereas with respect to the stronger ligand, since it got paired up, only two electrons will contribute for the spin. That's why it is forming a low spin complexes. So just to wrap up, the weak field ligand, the delta splitting is going to be smaller. Hence, it will form high spin complexes. Whereas this very strong field ligand, okay, it will just form low spin complexes because pairing is preferred. So as I said, this is a D4 system. The third electron, the fourth electron, in the case of weak field ligand, it just occupies up, so it forms four unpaired electrons. Whereas in the case of stronger ligand, you see the pairing of electrons. So this is a very standard representation of octahedral complexes splitting, but we will come to that point a bit later because it has a comparison between octahedral and tetrahedral complex. So we have two different set of calculations which is in your syllabus. One is CFSC, crystal field stabilization energy, and calculation of spin only magnetic moment. Okay. So we have, as I said, d electrons. We have d0 to d10 system. Okay, d0 there is no meaning because there is no electron. So d1 to d10 is all we will consider. So for example, in this particular slide, I have compared the number of electrons, how the electrons will be filled when you have a weak and strong field ligand, and how your crystal field stabilization energy. So this is the formula for calculating crystal field stabilization energy. The negative charge is a stabilization effect, that is 0.24. So how many number of electrons present, okay, in the T2G orbital? Either it could be on the plus half or the minus half of the spin, it doesn't matter. So the number of electrons in the T2G orbital multiplied by 0.4, that will give the stabilization number. Whereas how many electrons are present in the EG, that will give you the destabilization number. Okay, so we will have a comparison how these CFSC can be calculated for the various D systems in the presence of stronger and weaker field. So if this is a D1 system, whether it is a weak field or strong field, so the first electron is going to occupy in the T2G. So it will have a stabilization of 0.4. So it doesn't matter whether it is a weak or strong, your CFSC remains the same. Okay. But what matters here is not the number, this delta O. So this delta O will be higher for the stronger field and lower for the weaker field. So when you put the delta O number, then the CFSC will change. So when you just keep this delta O as a aside, so the numbers remains constant for both weak and strong field. Okay. D2 system, again it is the same. Two electrons in the T2G is going to be stabilizing in both the cases, weak and strong field. Okay, in D3, again the same thing. There is no change with respect to the strong or weak ligand. But always remember the delta O is a variation from complex to various complex to complex. Hence, these values will change. So this is minus 0.4 D1, D2. All you have is minus 0.8, whether it is weak or strong. In both the cases, this is the scenario. In D3, you have minus 1.2 as a stabilization factor, CFSC stabilization. For example, now in this case, we have 4 electrons. So as I said in the earlier slide, when you have the 4 electrons, this is a strong field. Okay, again, where you have the delta O is higher. This is weak field. The weak field, the fourth electron tends to go up. Okay, now we have 3 stabilization, that is 3 times 0.4 and 1 destabilization of 0.6. So net to net you have a 0.6 stabilization delta O. This is for high spin. High spin complexes always comes from weak field ligand. Low spin complexes always comes from stronger ligand. So because the strong field ligand, the splitting is so high, okay, so the fourth electron will not prefer to go up, that is to the dxy square minus y square or the dz square. Rather it will just tend to pair up. Okay, so here in this case we have a stabilization of 4 electrons from T to G orbital. We have 4 times 0.4, that is 1.6 delta O, but always you have a one pairing energy when it comes for the low spin complexes. So in D4 there is a difference in terms of CFSC, that is 0.6 delta O stabilization for high spin compared to 1.6 delta O for the low spin complexes. So D1, D2, D3, there is no change or there is no difference between weak and strong field. D4, we have a significant change in the number. Okay. So when it comes for D5 system, so in this case D5, 3 electrons is stabilizing. So if that is 1.2, whereas 2 electrons is destabilizing to the magnitude of 0.6. So whatever it is stabilizing, this will destabilize. So the net CFSC is only 0. There is no stabilization basically when you have a D5 electron system in the presence of weak field ligand. Okay. Whereas in the strong field ligand, all the 5 electrons will be in the T to G state because the pairing is not feasible. So we have 5 electrons in T to G. So we have the net to net 5 times 0.4. It will give 2 delta O stabilization. So there's a case with D6, the weak field ligand will have 0.4 stabilization, whereas in the case of strong field, all the 6 electrons are occupied in the T2G. So this is a maximum CFSC one can expect for a given complex, that is 2.4 delta O. T7, for the weak field complexes, you have 0.8 delta O, whereas for the strong field ligand, you have a stabilization of 1.8 delta O. So these are the numbers which are just we have it here. So what happened to for example, what happened to D8 system? Okay, if you are talking about D8 system, this is something for both the strong and field ligand and the weak ligands. The number of electrons occupied in the T2G and the EG remains the same. Okay, so for D8, for D9 and D10, for all the 3 systems, the CFSC for both strong and weak ligand remains the same. This is in analogy with whatever we looked at the D1, D2, D3. So you take from D1 to D10, D1, D2, D3, D7, D8, D9, D10. There is no significant difference between a weak field and a strong field ligand, except there is a magnitude change in the delta O. Whereas for D4, D5, D6, D7, there is a considerable or substantial difference in terms of CFSC stabilization energy. So similarly, since we know how in the weak field ligand how to arrange the number of electrons, in the strong field ligand how to arrange the number of paired or unpaired electrons. So based on the unpaired electrons, so the spin only magnetic moment comes only from the unpaired electron. So when there is a spin pairing, it already cancels the spins, so you will not have a net spin. So to have a spin only magnetic moment, you should always consider the unpaired electrons, that is number of unpaired electrons. So the formula for calculating spin only magnetic moment is root of n into n plus 2, where n stands for number of unpaired electrons present in the given D system. So for CFSC and for spin only magnetic moment, you should first know that whether this particular complex is a strong field ligand or a weak field ligand, or whether it is going to have a low spin complexes or high spin complexes, depending on it. It's not that always you should go with the ligand. If we also compare the oxidation state, let's say cobalt 2 plus and cobalt 3 plus. So cobalt 3 plus is going to have a low spin complexes compared to the cobalt 2 plus, which will have a high spin complexes. So based on the 4 parameters which will affect the d orbital splitting, So you need to identify whether it is going to be a high spin or low spin type complexes. Based on that, we need to arrange the number of electrons in the both T2 and EG orbitals. So this will enable you to do flawless calculations with respect to CFSE and spin only magnetic.